Now in order to build this common drain, like where do I apply my input and where do I tap my output in the case of a common drain? The input has to be across the gate, but the output is taken from the source, okay? So now then where do I fix my drain then? To the AC ground? Yeah, that is a better answer. So in short, it will be, if at all, if I'm going for an NMOS, then the drain will be connected to the capital VDD, and that when I translate to a small signal model, this drain would then translate as AC ground, right? So across the source, I have to tap my output. So whenever you want to tap an output, can this source could be connected to the ground? No, because this transfer will generate only the ID. But if at all, if I want a voltage, you have to pass through a load, okay? I've seen many people missing out this, directly tapping this as my output. That is not at all possible, okay? So you need to pass this current that you have generated from the transistor through a load. It could be a resistive load or it could be anything, okay? So let us take a resistive load and then we'll do it, okay? So this is known as a common drain amplifier, okay? Now this common drain also has a special name which you had just now, yeah. It's also called as a source follower, and we discussed more about it, so I will not go much in depth. So in general, this common drain configuration has two type of structures, one with resistive load, the other one is with the current source load, okay. Now shall we try to plot the relation of Vout versus Vin for this? Now how will I plot this? When I reach to the value of Vin that is equal to VDH, what is the value of voltage that I will have? 0, right? Because no current would flow. So there is no enough value of VGS here, due to which the capital ID would then goes to 0, and when no current is flowing, what is the voltage that I will have here? 0, okay? So any potential that I have here, that will be translated here, okay? So it will be 0, and after then what is happening is that initially there will be a kind of small slope, but after then it will be a very straight line just because it's a source follower, okay? And this is the kind of straight line, not a line like this. Yeah. So this is how you get it. So now let us try to evaluate the gain of this particular circuit, and this circuit is basically the resistive variant of common drain, okay? And later we'll replace this RS with current source load. But as of now, I just want you to calculate the small signal gain. Yeah, so got the answer? So what was the gain V out by Vn? First of all, is it a inverting or non-inverting? Non-inverting. You should get a positive value of Gm, okay? Now, did you get the value of Gm? What we do when I try to compute the capital Gm? I short the output node to the ground. So when I do so, nothing would go through this RS, okay? So this will not be there. But what current is flowing here? It is the ID. So what is this ID? How is it related to Vn? Gm times that of VGS, right? So the capital Gm would be exactly equal to Gm1 itself, if at all, if this is M1, okay? No change. The only thing is that it is no more a negative quantity, but rather it's a positive quantity. Clear? Yeah. So what about the R out? So again, when I look down, I'm looking as a RS value, okay? When I look upward, I have 1 by Gm1 parallel with RO1, and if you want body effect, we can just put a prime here, and then everything goes in parallel with RS. Okay? So you just multiply both these quantities to get the answer of gain. But rather than going like this, I just now spoke about the impedance seen from the source terminal, am I right? So I will use that concept to build this expression over here. Whatever the impedance that I am seeing towards the source is nothing but 1 by Gm in parallel with GMB in parallel with R0, okay? So when I translate this in terms of small signal, the drain is connected to my ground, so I connect that, but the gate is connected to my Vin, so I substitute the small signal Vin here, and then the source end is connected to RS, and this is my V out, okay? Now, how will I map these resistance value, all these three resistance value? So again, what I have is that 1 by Gm is always falls between the gate and the source, so I put that here, and 1 by GMB falls between the gate and the body, sorry, between the source and the body. Since the body is already at the ground, I just put as 1 by GMB. And then what about R naught? It falls only between source and the drain, right? So I just put that as well as R naught. Okay. So now what type of circuit is this? You see that RS 1 by GM and R naught, how are they connected to the source? They are in parallel. So I have a simple voltage division between V out and V in, right? So this circuit has something like this, where I am reading at this point V out, and at the input I am feeding my input V in. So the value of this is something like this, right? So yeah, so now that when I try to manipulate this, the V out is nothing but V in into this term, which is 1 by Gm in parallel with Rs, divided by 1 by Gm okay. So just manipulate this, you end up having the same result. So V out by V in should get me the same result that I did earlier. Okay. Does it make sense? Just by looking the entire circuit in a different perspective, I can just step down this entire formula into something like this and get the answer. So let me have some quick questions here based on the circuit that we have drawn. Yeah. So calculate the gain of the circuit by making use of this voltage divider method that I have just spoke about. So got the answer for this? I think it's a pretty simple. The only thing that we have is in the place of Rs, I have R naught. Okay, so everything else remains the same. In the last class, we discussed about this common drain amplifier, and it also had a special name, which is known as source follower. And based on this name, we can also plot a V out versus V in. Okay, so till VTH, the V out was 0, and then we had a graph something like this, right? And from the Cara, it is also possible for us to tell that the gain that I am going to get would be inverting or non-inverting. It's a non-inverting, just because when I rise my input, the output is also rising. So there will be a non-inverting, and the slope value will also be a positive value. Okay, yeah. So, and what we did is we try to feed the input towards the gate, and then we had two type of loads. Only one of them I addressed. I took the load as RL, and I took the output terminal from the source terminal. Okay, so this is the circuit that we had, and we also had said in order to compute this gain, there is a quick way to do that, right? So what is the way by which I can quickly compute the gain of this particular circuit? What did that we do? Yeah, we try to use voltage divider, just because when I look through the source, there is something, a new perspective I can get it, right? Because since I'm taking the output or tapping the output from the source terminal, rather than drawing all small signal models and then work out this entire transistor, what I can do is that I can just replace this transistor with some sort of resistive network, and for which we supposed to know what is the resistance that I'm seeing when I look through the source, and that answer would be like 1 by Gm parallel with 1 by GMB in parallel with R naught. Now all of these three resistance are connected to the source, but the other end of those resistance are not connected to the same terminals. Okay, so what we found is that this 1 by Gm is one that connects between the source and, yeah, so gate and source, and this was connected between, yeah, body and source, and this was connected between drain and source. Okay, so that is how we visualize the entire phenomena, and then we try to utilize our voltage divider rule to get down to this gain expression. So when we do so, we actually ended up having something like this, where I have something like 1 by GMB parallel with R naught parallel with RS or RL in this case, and I have this 1 by GM. This whole top term has to be repeated here. Yeah, so when I look into this formula, I couldn't able to get the the entire insight into this particular formula. So what I do is that I'll just try to combine each of these 3 parallel resistance as a single resistor value. Let me label that as RL prime. Okay, so RL prime is nothing but this entire quantity that I have in parallel. So divided by this 1 by Gm and then RL prime. Okay, so now when I do this manipulation, what we would get is something like, and now that I just want to refine this entire formula by expanding this RL prime again. So I will leave that particular task to you. You have to further expand this into the formula, and we have to get down to the final expression. Okay, so I'll just leave that to you people, but I just want to write down the final expression such that we'll try to infer some results, okay, or at least try to gain some sort of insight with respect to this formula when compared to what is known as common source amplifier with source degeneration. I just want to make a comparison. Okay, so I'll just write down the final result. This is the gain expression that I would get for the common drain amplifier. Now, what was the gain expression that we got for a CS amplifier with source degen? So what was its formula? There was a negative sign. Obviously, that is the difference between this formula and the common drain. Apart from this, yeah, it was almost similar, Gm R naught, and at the top we had something like Rd. There was a resistance, right? We had a resistance Rd, and then there was a resistance Rs, and we had input here and an output here. Okay, so due to which, when I try to write it, what I would get is Rd plus this impedance, which was taken as Rx. Okay, and the expression for Rx is nothing but R naught plus Rs plus Gm prime times that of Rs R naught. Okay, so this is a whole lot of expression. Okay, so now that I just want to compare this result with this result. So you could be able to see almost identical structures that we had, except for a few things. One is this RL I had at the top, whereas in this case it was RD. Okay, there was a drain resistance, whereas for this structure that I have, there is no drain resistance. Obviously, there is no drain resistance in this case, but in that place, what I have is the source resistance or the load resistance RL. Clear? And also, what is this expression basically? It is just the Rx value, right? So what I have is basically just Rx, whereas in this common source with source degen, what I have extra is this RD term. Okay, so that's the only difference that I could make out between these two formulas. Okay, so otherwise the formula is almost identical. If you could able to remember one of the formulas, you can do the other way. Okay, yeah. Now let me do some simplification on this formula in order to get some sort of insight. Okay, so I'll just do some simplification on the formula that I've written for the common drain and look for some sort of insight into it. Now what happens for these expressions when I have lambda equal to 0 and gamma equal to 0? Okay, so this is what I want to compute. What happens right now? If you could be able to recollect the previous formula that I wrote, which was RL prime divided by 1 by Gm plus RL prime. So now what happens to this RL prime when I use these conditions on this? So there was 1 by Gm in parallel with 1 by GMB in parallel with R naught. So what happens to these components when I have these two values? They step down to, so this GMB will become 0. So 1 upon 0 is infinity. So I have infinity here in parallel with one more infinity, and that goes, entire infinities goes in parallel with 1 by Gm. So what I would get out of this RL prime is effectively, am I right? I think RL I have to write, right? Sorry. Yeah. So this entire formula would then steps down something like RL, and I will also do some cross multiplication of this Gm. Okay. Now, let us try to plot a gain versus Vin. Let us try to understand what is the maximum gain that we would get out of this particular structure. Okay. So, Now, initially, when the value of Vn is less than Vt, what happens to my gain? Will there be any gain in the circuit? No, just because what is happening to my circuit here, Gm is basically proportional to Vgs minus Vt, and the moment it goes in the negative direction, obviously the current won't be there. In general, the Gm is equal to 0, right? So what happens after this? The moment I cross this Vt, what happens to the gain? Yeah, so at the earlier stage, the value of Gm would be quite smaller because the value of Vn is small here, okay? So due to which this quantity plays a role. Even the denominator of 1 plus Gm, the one quantity or this quantity would be larger than compared to this guy, okay? So initially it starts increasing. But after then, what happens to this Gm? As I increase the value of Vn further and further, what happens to this Gm? Gm increases, and due to which this quantity, yeah, no, not to be constant, but the point is that this quantity also grows along with this Gm, right? So at a particular point, the value of this Gm RL would then predominantly higher than the value of 1. So one could approximate this entire expression as something like Gm RL divided by Gm RL itself, right? And that leads to 1. Just because the Gm has got rise, so what is happening is that my Gm RL becomes way larger than the value of 1, okay, as I increase the value of Vn, and due to which we have a maximum gain of 1, and that is the condition that I have when I feed this as my input assumptions, okay. So I have this lambda and gamma that is equal to 0. Now what we do is that we will try to leave out one of the assumptions that we have made, that is I will just try to bring down the value of gamma not equal to 0. Now what happens to the formula? I'll just make this, yeah, something else has happens here, okay. So yeah, Gm prime, but will I get Gm prime out of this RL prime or out of this Gm itself? Yeah, it comes with RL prime, okay, because as I said before, this RL prime was 1 by Gm, 1 by GMB, yeah, and in parallel with, sorry, yeah, I always do this mistake, yeah, so we have this RL and R naught, yeah. So you can able to see that this 1 by GMB is a factor that is associated with this RL prime, okay. So do not try to put Gm prime here, okay, that is not the proper answer, but the whole point is that I'll just write down the final value, that the gain would then be approximated as something like 1 upon 1 plus eta, okay. There is a factor eta that appears just because of this RL, okay. So I will not do this derivation, or I will not step down this derivation to show that this is the value. So again, you have to expand this equation into the formula, and then you would get the same result, clear? So my maximum expectation for a common drain amplifier with a residual load is basically 1. That is the maximum gain that I can get out of the circuit. But when I have this gamma effect or the body effect, the gain never reaches this 1, but rather the value that it can reach is always less than the value of 1 just because of the factor eta. Is that clear? So those are the graphs that I just wanted to plot based on this. So now what we do is that let us also see that just because this eta, does it introduce some sort of nonlinearity into my circuit, the factor eta? So what is this eta? I want in terms of DC parameters, gamma divided by 2 into root over 2 phi f plus VSB, right? So there is a VSB term, and we know that the source node is basically my Vout node. So whenever there is a change in my Vout, the VSB would change. In turn, the gamma introduces some sort of nonlinearity into my gain expression, which we don't want, right? So, but we cannot avoid it just because the structure is so. The only way that I can do, I can avoid this gamma effect is by introducing some sort of short between the body and the source terminal, but for which you have to spend a lot of money in order to fabricate such type of well, okay. So if you don't have money, then you have to work with this nonlinear effect. Now the whole point is that why do I need this circuit? What is the need of this common drain? As I know that the maximum gain that I can get out of the circuit is just 1, but yeah, it can be used as a buffer. Now what is this buffer and what is the need of it? Say for example, I have designed a very high gain circuit, let us take our simple common source amplifier. I have done something here in order to get a very high gain. Will not worry about whether I worked with RD or I worked with W factor. But the whole point is that I have got too much of gain out of the circuit. Now I have a load to the device, okay, and that load is basically a very small resistance load. Now what happens the moment I connect this load directly to this structure, CS amplifier? Okay, let me replace this guy with the current source load because, yeah. Okay, so I have a very high gain out of this structure, CS amplifier, okay, but the moment I connect this small resistive load, what happens to the gain of the circuit? Yeah, yeah, so we know that the gain of the circuit is always defined as GM times that of R out. Now, the R out that we have computed earlier was just RO1 in parallel with RO2. The moment I feed this RL in parallel, the entire R out would then step down, due to which the gain of the circuit steps down, but which we don't want. So how will I avoid this situation? By introducing a buffer between the RL and this output of my CS amplifier, okay. So just add a small buffer, and this buffer is nothing but our common drain amplifier, okay. It doesn't do any amplification, but the sole purpose of this amplifier is just to ensure to separate my low resistive network from the high resistive network, okay. So that is its task. Now it also has some sort of drawback. I don't know whether to discuss. Do we have enough time? Let me try. Now, how will I define this output Q point here? So I just want V out Q. Why so much of thought process is happening? I think it's supposed to strike you well before. Okay, let us forget about this circuit that I have here. Okay, so let us assume that there is some sort of VB here. Okay, we will go with this circuit. Okay, yeah. So for this circuit, yeah. So something is falling across my gate and source of my circuit, right? So basically, the V out Q is defined as VB, which is the potential that I have between this gate and the ground, okay, and that has to be subtracted here by the corresponding value of VGS. Am I right? So what I have is nothing but VB minus the VGS2 circuit, okay, and this VGS2 circuit basically is defined by the DC current that is flowing through this particular path, right? Yeah. So now the whole point is that it purely depends. The output can swing. What is the maximum value that it can swing over this Q point defined value? I can have a maximum swing which can go all the way till VB minus VDH. That is the maximum that you have. Okay, you cannot go beyond that. Okay, what is the minimum? Is there any restriction like this? No. So the only thing is that I need to consider the VOV of this transistor, so which is what we had right from the earlier stage, so VOV of 3. Okay, so now how would we choose this value of VB such that I will have a maximum swing around it? Can we, so we will try to push the value of VB to higher value which is closer to the value of VDD. That's how I can have a maximum swing at the output, right? Otherwise, if I'm fixing the value of VB to VDD by 2, what happens is that the output swing is basically being reduced just because the VB value is getting reduced, right? Okay, so there is a limitation when you try to cascade the circuit with other circuit. The limitation comes back to you, hit back worstly in defining the output swings.